All right, so we're going to try to understand a little bit about how to make Bode plots in Matlab. There's basically four things that we're going to go through. So first is trying to figure out how to place the transfer function into Matlab. All right, and then figuring out how to create the Bode plot. Then trying to figure out how to change the frequency limits and using the plot to find specific values on the Bode plot. And then learning how to plot more complicated transfer functions. Okay, so let's go straight to it. Let's take an example. Let's say I've got h1 of s equal to 3 over s squared plus 3s plus 1. The way that we do this in Matlab is we basically recognize that the transfer function is always a rational function of s, which means that both the numerator and the denominator are polynomials in s. And what I need to do is to create two vectors, one vector having the coefficients of the s variables on the numerator, and one having the coefficients for the denominator. So to do this, for this type of function, what I would say is that the numerator in this case is simply a vector with one entry, 3. Okay? And the denominator is a vector with 3 entries, and I always start with the coefficients that are on the highest order term, and then I do them in descending order. So in this case, on the squared term, which is the highest order term, I have a 1. On the first order term, I have a 3. And on what I call the 0th order term, or the constant term, I have a 1. Okay? So at that point, I am completely done, and I can write this guy and pass it into Matlab. The way that we typically do that is I usually write a function sys, and I use the transfer function command tf, and I pass to that the numerator and the denominator. And then I can type Bode of sys, and it will create the Bode plot that corresponds to this guy. And Matlab will automatically choose a range of vectors, and by default it is going to plot versus omega, not f, but omega. Alright, so that's pretty straightforward. Let's take a look at an example. Alright, so here's an example code. Alright, so up here in part 1, I have num1 equal to 3, den1 equal to 131, so it's exactly what I've created here. All right, I say sys equals num1 den1 of tf, so I created the transfer function. And then notice I say figure 1 and then Bode sys, which forces it to be in figure 1. Otherwise, if you run Bode, it just automatically plots in whichever figure you used last. All right, so I'm going to run this guy. And there it is. It updates. Okay, so I can see that I've got my Bode plot. Now, one of the things that I might want to do is to read values out of this thing. You'll need that in your assignments. So I go to my data tips. I hover over this guy, and then I can move the mouse along. Now, I notice from this, one thing that can be a little bit frustrating is even if I just click ahead, I'll see there's big jumps that happen. If I'm looking for a particular frequency, I might want finer jumps. So one of the things I can do is hover over this data tip and then right click, and I can say selection style. It says snap to nearest data vertex. Well, one thing I can do is I could say click mouse position. Okay, so when I do that, it basically, wherever my mouse goes is what it gets, right? So this now is much finer grain than I had before. All right, if I look at what this guy is doing, I actually see that I can get all the way down to 1/10 of a frequency accuracy. Okay. All right, so this turns out to be really useful. All right, once I've changed it for one of the graphs, I've changed it for the other one. All right, this turns out to be really useful if I want to figure out, okay, well, for this particular system, sys, at a frequency of 0.892 radians per second, the phase shift is negative 110 degrees. I can use that in my analysis. Okay, let's say for whatever reason that I wanted to see more than what I have here. In other words, I want to see from the frequency range 10 to the minus 3 to 10 to the 4th. Okay? Let's say I wanted to see that. Well, if I did, I can use this command right here. Right? I get this by typing help Bode, but I basically see that I can tell it the frequency range to go from 10 to the minus 3 to 10 to the 4th. And I notice here that these guys are in squiggly brackets. That may be hard for you to see, but it's squiggly brackets. And if I really want to see that, I can always type help Bode in Matlab. And I can scroll through that and say, I see squirrely brackets W min, W max, draws the Bode plots for frequencies between W min and W max. Okay? All right. So I'm going to go ahead and run that command, and we're going to see that my plot here, which now goes from 10 to the minus 2 to 10 to the 2, is going to expand. So I'll evaluate selections, and there it is. Right? This guy starts now all the way over at 10 to the minus 3, or 0.001, and he goes all the way over to 10 to the 4th. Okay? All right, so pretty easy to see how to extend the range of this guy. Now let's look at a more complicated transfer function. All right, so let's say I've got this guy, 3 times s plus 1. So I've got something on top, and then I've got two polynomials down on the bottom. All right, Matlab has a pretty simple tool for calculating when I have two polynomials that I'm foiling, right? So if I'm doing polynomial multiplication, what you learned in high school is foiling, right? There's a way of doing that in Matlab using the command conv, C-O-N-V. All right, so I took this example here right off of the Matlab website. So it says, in this case, I've got x squared plus 1 and 2x plus 7. So notice what they did here. So they defined this guy as u. Oops, not w. This guy here is u. This guy here is v. So basically, because I have x squared plus 0x plus 1, they mapped that to 1, 0, 1. Okay? So notice the 0 in the middle to say that there is no first order term. And then 2x plus 7 becomes 2, 7. Okay? And here's that definition right here. To multiply those guys out, I do this conv, C-O-N-V, u comma v, and then I end up with the result. So this guy w that I get, so 2, 7, 2, 7, like that. The last entry here is always the 0th order term, or the constant. This guy is always the first order term, second, and then this guy is the third order. If there was another entry in front of it, it would be the fourth order term. So I see that this guy becomes 2x cubed on the third order term. I see I have a 7 on the second order term, a 2 on the first order term, and a 7 on the constant term. All right, so if I wanted to do this problem, what I would say is I'd set my numerator equal to 3 times 1, 1. Right? That basically creates the coefficient vector I need. Okay? In the denominator here this time around, I'm going to use that conv function, and I'm going to say I'm going to take this vector here, or that polynomial, and turn it to 1, 3, 1. And I don't put a colon there, no, I put a comma. And then I take this next guy here, which has coefficients 1, 3, 2, like that. All right. Now I'm ready to go. I can put that into Matlab. And that is exactly what I have here in part 2. Right? So I have that conv function, save it to a system using the transfer function, and plot it. So then I'm going to evaluate the selection there, and there it is. All right, and like before, if I want to be able to play around with the ranges, I can. I can, if I want to get more complicated, I can even tell it the frequencies exactly that I want it to plot at. All right, you can type help Bode to do that. But the information that's provided here should be sufficient for you to be able to figure out what you need to do.